In this video, we're going to cover what is arguably the single most important concept in all of statistics. And maybe, well, I mean, if you go into almost any scientific field, you might even argue it's the single most important concept. And I've actually told people that it's kind of sad that they don't cover this, in the core curriculum. Everyone should know about this because it touches on every single aspect of our lives, and that's the normal distribution or the Gaussian distribution or the bell curve. And just to kind of give you a preview of what it is, and my preview will actually make it seem pretty strange, but as we go through this video, hopefully you'll get a little bit more of an intuition of what it's all about. But the Gaussian distribution or the normal distribution, they're two words for the same thing. It was actually Gauss who came up with it. I think he was studying astronomical phenomenon when he did. But it's a probability density function, just like we studied the Poisson distribution. It's just like that. And just to give you the preview, it looks like this: that the probability of getting any x, and it's a class of probability distribution functions, just like the binomial distribution is and the Poisson distribution is based on a bunch of parameters, but it's equal to. And this is how you would traditionally see it written in a lot of textbooks. And if we have time, I'd like to rearrange the algebra just so you get a little bit more intuition of how it all works out, or maybe we could get some insights on where it all came from. I'm not going to prove it in this video. That's a little bit beyond our scope, although I do want to do it. And there's actually some really neat mathematics that might show up in if you're a mathlete, there's something called Stirling's formula, which you might want to do a Wikipedia search on, which is really fascinating. It approximates factorials with essentially a continuous function, but I won't go into that right now. But the normal distribution is 1 over, this is how it's normally written, the standard deviation times the square root of 2 pi times e to the minus 1/2. And I like to write it this way, it's easier to remember, times whatever value we're trying to get minus the mean of our distribution divided by the standard deviation of our distribution squared. And so if you think about it, actually, just is a good thing to just notice right now. This is how far I'm from the mean, and we're dividing that by the standard deviation of whatever our distribution is. And this is a preview of actually a normal distribution that I've plotted. The purple line right here is a normal distribution. And just so you know, the whole exercise here, I know I jump around a little bit, is to show you that the normal distribution is a good approximation for the binomial distribution, and vice versa. If the binomial distribution, if you take enough trials in your binomial distribution, we'll touch on that in a second. But it's the intuition of this term right here, I think, is interesting, because we're saying how far are we away from the mean. We're dividing by the standard deviation. We're saying, so this whole term right here is how many standard deviations we are away from the mean. And this is actually called the standard z-score. One thing I found in statistics is there's a lot of words and a lot of definitions, and they all sound very fancy. The standard z-score. But the underlying concept is pretty straightforward. Let's say I had a probability distribution, and I get some x value that's out here, and it's 3.5 standard deviations away from the mean. Then its standard z-score is 3.5. But anyway, let's focus on the purpose of this video. So that's what the normal distribution, I guess the probability density function for the normal distribution looks like. But how did it get there? I guess even more importantly, I want, by the end of this video, you should at least feel comfortable that this is a good approximation for the binomial distribution if you take enough trials. And that's what's fascinating about the normal distribution, is that if you have the sum, and I'll do a whole other video on the central limit theorem, but if you have the sum of many independent trials, approaching infinity, that the distribution of those, even though the distribution of each of those trials might have been non-normal, but the distribution of the sum of all of those trials approaches the normal distribution. And I'll talk more about that later. But that's why it's such a good distribution to kind of assume for a lot of underlying phenomenon if you're kind of modeling weather patterns or drug interactions. And we'll talk about where it might work well and where it might not work so well. Like sometimes people might assume things like a normal distribution in finance, and we see in the financial crisis that's led to a lot of things blowing up. But anyway, let's get back to this. And this is a spreadsheet right here. I just made a black background, and you can download it at, let me write it right here, at khanacademy.org. khanacademy.org downloads. And actually, if you just do that, you'll see all of the downloads. I haven't put it there yet. I'm going to do it right after I record the video. This downloads / normal distribution, that's distribution.xls. If you just go up to khanacademy.org/download/, you'll see all of the things there, and you'll see that this spreadsheet. And I encourage you to play with it and maybe do other spreadsheets where you experiment with it. So this spreadsheet, what we do is we're doing a game where, let's say I'm on a street, and I flip a coin. I flip a completely fair coin. If I get heads, let's say this is heads, I take a step backwards, or let's say a step to the left. And if I get a tails, I take a step to the right. Right? So in general, I always have this is a completely fair coin. I have a 50% chance of taking a step to the left, and I have a 50% chance of taking a step to the right. So your intuition there is, if I told you I took 1,000 flips of the coin, well, you're going to keep going left and right. If by chance you get a bunch of heads, you might end up really kind of moving over to the left. If you get a bunch of tails, you might move over to the right. And we learned already that the odds of getting a bunch of tails, or many, 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 many more tails than heads, is a lot lower than things kind of being being equal or close to equal. And right here, what I've done, let me turn into the let me scroll down a little bit. Okay. I don't want to lose the whole thing. All right. So what I've done right here is I have this little assumption here, and I encourage you to fill that out and change it as you like. This is the number of steps I take. This is the mean number of left steps. And all I did is I got the probability, and we figured out the mean of the binomial distribution. The mean of the binomial distribution is essentially the probability of taking a left step times the total number of trials. And so that's equal to 5. That's where that number comes from. And then the variance, and I'm not sure if I went over this. I need to prove this to you if I haven't. I'll make a whole other video on what on the variance of the binomial distribution. But the variance is essentially equal to the number of trials, 10, times the probability of taking the left step, or kind of a successful trial. That's what I'm defining left as a successful trial, but it could be right as well, times the probability of 1 minus a successful trial or non-successful trial. In this case, they're equally probable, and that's where I got the 2.5 from. And that's all in the spreadsheet. If you actually click on the cell and look at the actual formula, I did that, although sometimes when you see it in Excel, it's a little bit confusing. And this is just the square root of that number, right? The standard deviation is just the square root of the variance. So that's just the square root of 2.5. And so if you look here, this says, okay, what is the probability that I take 0 steps? So I take a total of 10 steps, just to understand the spreadsheet. So if I take a total of 10 steps, what is the probability that I take 0 left steps? Well, and just to clarify, if I take 0 left steps, that means I must have taken 10 right steps. And I calculate this probability, and I should have drawn maybe a line here. This is the binomial. I calculate this using the binomial distribution. And how do I do that? Well, I say, what is the probability that I take? Well, I take a total of 10 steps. So let me actually switch colors just to make things interesting. Let's see, do they have a purple here? I'll do a blue. So the blue for binomial. So what I have here is how many total steps? I'm going to take, so there's a total of 10 steps. So 10 factorial. That's kind of the number of trials I have. Of that, I'm choosing 0 to go left. So 0 factorial divided by 10 minus 0 factorial, right? This is 10 choose 0. I'm choosing 0 left steps of the total 10 steps I'm taking, times the probability of 0 left steps. So it's the probability of a left step. I'm only taking 0 of them, times the probability of a right step, and I'm taking 10 of those. So that's where this number came from, this 0.001. That's what the binomial distribution tells us. And then this one, similarly, is 10 factorial over 1 factorial over 10 minus 1 factorial. And that's how I get that one. And once again, if you click on the actual cell, you'll see that explained. So we've done this multiple times. It's just the binomial calculation. And then right here, after this line right here, you can almost ignore it. And I did that so that I can do a bunch of different scenarios. So for example, if I were to go to my spreadsheet, and if instead of doing 10 steps, I wanted to do, whoops, I should use it. If I were to do 20 steps, then everything changes. And that's why down here there's, after you get to kind of a certain point, the whole thing just kind of repeats. And I'll let you think about why I do that. Maybe I should have made a cleaner spreadsheet. But it doesn't affect the scatter plot chart that I did. And so this plot in blue, and you can't see it because the purple is almost right over it. Actually, let me make it smaller so that you can see. So if I only took, let's say I only took 6 steps. Well, it's still hard to see the difference between the two. And then once again, the whole point of this is to see that the normal distribution is a good approximation, but they're so close that you can't even see the difference on my. See, if you only took 4 steps, okay, I think you can see here, the blue here is definitely. Let me get my screen drawer on. So let me draw this. The blue curve is right around there, right? So this is the binomial. There's only a few points here, right? The points only go up to here. This is if I take 0 steps left, 1 step left, 2 steps left, 3 steps left, 4 steps left, and then I plot it, and then I say what's the probability using the binomial distribution. And then this is my final position, right? If I take 0 steps to the left, then I take 4 steps to the right, so my final position is at 4. So that's this scenario right here. Let me switch my color back to yellow. It's easier to see. Yellow. If I take 4 steps to the left, I take 0 steps to the right, and so my final position is going to be at -4, right? It's going to be here. If I take an equal amount of both, so that's this scenario, then I'm neutral. I'm just stuck in the middle right here, right? I take 2 steps to the right, and then I take 2 steps to the left, or vice versa. I take 2 steps to the left, and then I take 2 steps right, and I end up right there. And so hopefully that makes a little sense of how this. Let me see, my phone is ringing. No, I'll ignore that. Because the normal distribution is so important. And actually, my 9-week-old son is watching, so this is the first time I have a live audience, but I thought he might pick up something about the normal distribution. But anyway, this is, so the blue line right here, and I'll trace it maybe in yellow just so you can see it, is the plot of the binomial distribution. And I connected the lines, but you see the binomial distribution looks something more like this, where this is the probability of getting to -4. This is the probability of going to -2. This right here is the probability of ending up nowhere. And then this is the probability. See, actually, no, the point is right here. This is the probability of ending up 2 to the right. And then this is the probability of ending 4 to the right. This is the binomial distribution. I just plotted these points right here. This is 0.375. This is 0.375. That's the height of that. Now, what I wanted to show you is that the normal distribution approximates the binomial distribution. So this right here, I wanted to say, what does the normal distribution tell me is the probability of ending up with exactly 0 left steps. And then this is a little bit tricky because the normal distribution, so the binomial distribution is a discrete probability distribution. You could just look at this chart or look here and you say, what is the probability of ending up to, having exactly, let's say, 1 left step and 3 right steps, which puts me right here. Well, you just look at this chart and you say, oh, that puts me right there. I just read that probability. It's actually 0.25. And I say, oh, I have a 25% chance of ending up 2 steps to the, what example was that? Oh yeah, 2 steps to the right. There's a 25% chance. The normal distribution function is a continuous probability distribution. So it's a continuous curve. It looks like that. It's the bell curve. And it goes off to infinity and starts approaching 0 on both sides. It looks something like that. But this is a continuous probability distribution. You can't just take a point here and you say, what's the probability that I end up 2 feet to the right? Because if you just say that, there's the probability of being exactly, and you should watch my video on probability density functions, but the probability of being exactly 2 feet to the right, exactly, I'm talking to the atom, is close to 0. So you actually have to specify a range around this. And what I assume in this is I assume that within essentially a half a foot in either direction. right? If we're talking about feet. So to figure that out, what I did here is I took the value of the probability density function there, right? And I'll show you how I evaluated that. And then I multiplied that by 1. So it gives me this area. And I use that as an approximation for this area. If you really wanted to be particular about it, what you would do is you would take the integral of this curve between this point and this point as a better approximation. We'll do that in the future. But right now, I just want to give you the intuition that the binomial distribution really does converge to the normal distribution. So what is this number right here? Well, I said, what is the probability? Well, let me do something like this. Let's say this one right here, because I don't want to use the 0. So what is the probability that I take one left step? I kind of used left steps as a success. So what is the probability of 1? And that equaled 1 over the standard deviation. When I only took 4 steps, the standard deviation was 1. So 1 over 1. Actually, let me change this because I think it might be, let me change it to a higher number. Let's see, if I make this, I don't know. Let me go back to the example where I'm at 10. All right. So if this is at 10, let me go back to my drawing tool. OK. So this calculation right here, no, let me do this calculation. Actually, even better, let me do this calculation right here. All right. So what's the probability that I have 2 left steps? And if I have 2 left steps, I took a total of 10 steps. So I'm going to have 8 right steps. And that puts me 6 to the right. So that's, this point right here. So what's that probability? How do I figure this out using the probability density function? How do I figure this out? Well, I say the probability of taking 2 left steps, that's how I calculate it. If you actually click on the cell, you'll see that, is equal to 1 over the standard deviation, 1.581. And I just directly reference the cell there. Divided times the square root of 2 pi. And I'll go on, I always go on in awe of the whole notion of e to the I pi is equal to -1 and all of that. But this is another amazing thing, that all of a sudden we have this, as we take many trials, we have this formula that has e and pi in it and square roots. But once again, these two numbers just keep showing up. And it tells you something about, I don't know, the order of the universe with a capital O. But let's see. So times e to the -1/2 times x. Well, the x is what we're trying to calculate. 2 successes. So to have exactly 2 left. So it's 2 minus the mean. So the mean is 5. 2 minus 5 divided by the standard deviation divided by 1.581. All of that squared. That's where this calculation came from. And so, if you really, so I told you in the last one, this just tells you, this right here just tells me this value up here. And I assume that the probability, if I want to know this exact probability, it's the area of this. And if I just take one line, the area is 0. So to be exactly 2 feet away using remember, in this case, you can only be 2 feet away because we're taking very exact steps. But what the normal distribution is, it's a continuous probability density function. So it can tell us what's the probability of being 2.183 feet away, which obviously it can only happen if we're kind of taking infinitely small steps every time. But that's where its use is. It happens kind of when you start taking an infinite number of steps. But it can approximate the discrete. And the way I approximate it is I say, oh, what's the probability of being within a foot of that? And so I multiply this height, which I calculate here, times 1. So, let's say this has a base of 1 to calculate this area, which I use as an approximation. So you just multiply that times 1, and that's what you get here. And I just want to show you, even with just 10 trials, the curves for the normal distribution here is in purple, and the binomial distribution is in blue. So they're almost right on top of each other. They started when the number of steps I took was a little bit smaller. And as you take many more steps, they almost converge right on top of each other. And I encourage you to play with this spreadsheet. And actually, let me show you that they converge. So I made there's a convergence worksheet on this spreadsheet as well. If you click on the bottom tab on convergence. And this is the same thing, but I just wanted to show you what happens at any given point. So let's say that I wanted to, let me explain this part, this spreadsheet to you. So this is, what's the probability of moving left, right? So this is just saying, I'm just fixing a point. What's the probability, and you could change this, of my final position being 10. And then this essentially tells you that if I take 10 moves, then for my final position to be 10 to the right, I have to take 10 right moves and 0 left moves. And that's a typo right there. It should be moves, not moves. If I take 20 moves to end up 10 moves to the right, then I have to make 15 right moves and 5 left moves. And likewise, if I take a total of 80 moves, if I take 80 flips of my coin to make me go left to right, in order to end up 10 to the right, I have to take 45 right moves and 35 left moves in any order. And it'll end up with 10 to the right. So what I want to figure out is, as I start taking, a bunch of total moves, it's like my total moves, I mean, here I max it out at 170, but you could kind of say, if I started flipping this coin an infinite number of times, I want to figure out what's the probability that my final position is 10 to the right. And what I want to show you is that as you take more and more moves, the normal distribution becomes a better and better approximation for the binomial distribution. So right here, this calculates the binomial probability, just the way we did it before. And you could look at the cell to figure it out. This says 10. I use left moves as a success. So this is 10 choose. This is 10 choose 0, and we know what that is. That's 10 factorial over 0 factorial over 10 minus 0 factorial times 0.5 to the 0 times 0.5 to the 10. That's where that number comes from. If I go to, let's say, this one right here is calculated. Actually, let me write it out because I think it's interesting. I have a total of 60 total moves. So it's 60 factorial over, I have to have 25 left moves. So 25 factorial times 60 minus 25 factorial times the probability of a left move, and I have 25 of them, times the probability of a right move, and I have 35 of those. Right? So that's where each of those, so that's just where what the binomial probability distribution will tell us. And then it figures out the mean and the variance for each of those circumstances. And you could look at the formula, but the mean is just the probability of having a left move times the total number of moves. The variance is probability of left times probability of right times total number of moves. And then the normal probability, once again, I just use the normal probability. I just use so I approximate it the same way. So for example, in this situation right here, and Excel has a normal distribution function, but I actually typed in the formula because I wanted to kind of see that, what was under the covers for that function that Excel actually has. So I actually say, what's the probability of 25 left moves? Oh no, let's see, no, 45 left moves. So I say the probability of 45 left moves is equal to 1 over the standard deviation. So in this situation, the standard deviation is the square root of 25. So it's 5 times 2 pi times e to the minus 1/2 times 45 minus the mean minus 50 over the standard deviation, which we figured out was 5 squared. So that tells me the value of what the normal distribution tells me for this situation with this standard deviation and this mean. And then I multiply that by 1. So you don't see that in formula. I don't actually write times 1 to actually figure out the area under the curve, right? Because remember, it's a continuous distribution function like that. This right here just gives me the value. But to figure out the probability of being within a foot of it, I have to multiply it by 1, or I'm approximating really. I really should take the integral from there to there, but this little rectangle is a pretty good approximation. And this chart, I show you that as the total number of moves gets larger and larger, the difference between what the normal probability distribution tells us and the binomial probability distribution tells us gets smaller and smaller in terms of the probability of you ending up 10 moves to the right. And you can change this number here. Let me change it just to show you. You could change it. You could say, oh, what's the probability of being 15 moves to the, no, I used the wrong tool. You could say, what's the probability of being 15 moves to the right? And actually, no, that one doesn't. 15 moves to the right. It looks like it kind of, no, that's not. Let's see, it's 10. And if I go 12, it converges. And then if you go to 13, I think that something's happening with the floating point error, because when you get to large factorials, I think something weird happens out here. But like if you do 3, something weird is happening. 5, 10. Yeah, you maybe have to just get even further out. So as for 10, you can see clearly that it converges, and I'll try to figure out why I was getting those weird sawtooth patterns. If you get 11, no, everything is, maybe while I do screen capture, something weird is happening. But anyway, the whole point of this was to show you that if you wanted to figure out the probability of being 10 moves to the right, as you take more and more flips of your coin, the normal distribution becomes a much better approximation for the actual binomial distribution. And as you approach infinity, they actually converge to each other. Anyway, that's all for this video. I'll actually do several more videos on the normal distribution just because it is such an important concept. See you soon.